Hi, and welcome back to Geology 1 Processes and Products. My name is Renee Clary, and today we will be discussing not only one, but three geologic agents that erode, transport, and deposit and modify the Earth's surface. This fits in very well with our three main themes of geology that we cover this semester: plate tectonics, the rock cycle, and finally uniformitarianism and the ancient age of Earth. Over time, our shorelines have changed and been modified by these geologic processes. Let's get started. When we talk about shorelines, specifically we're talking about the area between high and low tides. Now, a coast is slightly different, and some people will disagree on the definition as how far a coast will move inland before it's no longer a coast. But more than half of the world's population lives along a coastline somewhere. So it's very, very important that we understand the processes and how they are changing shorelines on Earth. Naturally, shorelines are affected by changes in relative sea level. In glaciation, we discuss how when ice accumulates on a continent, the sea level will drop. When that ice subsequently melts, sea level will rise. So shorelines are affected by Earth processes and can fluctuate very greatly over time. Shorelines can migrate landward if the sea level rises, or they can migrate seaward if the sea level falls. We're going to look at different shoreline processes today, geologic agents that erode, transport, and deposit. Specifically, we're going to look at tides, waves, and nearshore currents. The first one we will look at are the tides. Tides are daily changes in the ocean's elevation. We're not talking about waves that are washing ashore. Instead, we're looking at the rise and fall of the ocean elevation. This is caused by gravitational attractions of the sun and the moon and Earth. Tides are dominated by the moon. Now, why is this? Why are tides dominated by the moon? If it's a gravitational attraction, the sun is so much bigger. Remember Newton's law of universal gravitation? The gravitational attraction is directly proportional to the mass of the objects. So if the sun is so much bigger, why doesn't it exert a greater force? Well, also remember that Newton's law of universal gravitation specifies that the gravitational attraction is inversely proportional to the square of the distance between the two objects. So the moon is so much closer than the sun, and it will dominate the tidal force. There are two high tides, a flooding tide process, and two low tides, or an ebbing tide process, that occur daily. Here we have the moon and the Earth, and that dotted line represents the force that will create the tides. Two bulges are created on the Earth's surface. One bulge will point toward the moon, and the other on the opposite side of the moon is produced by centrifugal force resulting from the Earth's rotation. So we have two bulges, one on the side of the moon and one on the opposite side of the Earth, away from the moon. This is low tide in Turnagain Arm, which is part of the Cook Inlet in Alaska. Look at the railroad track in the right foreground. Low tide, high tide at Turnagain Arm. Now, the sun has some gravitational pull, even though the moon dominates. We can have spring tides, though, when the combined gravity of an aligned sun and moon produce higher flood and lower ebb tides. So we're going to have a larger displacement, a larger range in a spring tide. This occurs at full and new moons. I'll show you an illustration of that next. The opposite of that is what is called a neap tide. The offsetting gravity, if the sun and moon are at right angles to each other and therefore their gravity is sort of canceling out a bit, we get less of a tidal range. So with a spring tide, we have a higher than high and a lower than low, a lower than average low. Whereas with a neap tide, we don't have much of a range because the gravity of the sun is sort of canceling some of the gravitational attraction from the moon. And this will occur at 1/4 and 3/4 moons. Let me show you that. Okay, here we have the moon, the new moon, which is between the Earth and the sun. And then the full moon is represented on the left-hand side of the diagram. Note the size comparisons. Of course, this is only for illustration purposes. It's not true to scale. The sun is huge, but it's so much farther away. However, when the sun and the moon align, they produce a greater tidal effect, and we have much stronger tides, much higher high tides and lower low tides. However, if the sun and the moon are at 90 degrees, this happens at a 1st quarter moon and at a 3rd quarter moon, then the moon's gravitational attraction will be counteracted by the sun and there will be less of a tidal range that is produced. This is a neap tide. So if we plot the tidal range on a calendar, for example, spring tides have the greatest range. And I have a spring tide up there in the upper left corner. There's another spring tide in the lower right. The neap tides have less of a range, and that's the chart that you see in the middle. Those are neaps. If we take one oscillation, the ebb tide is when the tide is going out, and the lowest of lows, there's our low tide, and then as the tide starts to rise, this is a flood tide, and the highest of highs is our high tide. Again, we get greater tidal range at a spring tide and less of a range when we have neaps. With tides, the shoreline shape will affect the range that is observed on the land. A broad continental shelf will have a lower range between high and low than if you have a narrow funnel-shaped bay or an inlet. Narrow funnel-shaped bays and inlets produce a greater tidal range. Let's look at a map of the United States. Okay, here we have in the Gulf of Mexico, this is a broad continental shelf, so therefore we would expect to see a smaller tidal range compared to, look at right off of California, Baja California, in that inlet, there is a large tidal range. The second shoreline process we will discuss today is that of waves. Now, waves differ from tides in that waves are undulations of a water surface. Tides are simply the rise and fall of the elevation of the ocean, whereas tides are the movement or the undulation of the water surface. Waves are responsible for most of the erosion, the transport, and the deposition along shorelines. Waves are caused by, we can have a wave produced by faulting underwater, such as that December 26, 2004 tsunami that was generated by displacement. Also, waves can be caused if an area of earth slumps or slides into a water basin. We can produce waves, but most commonly, waves are produced by wind. We're going to look at a diagram of a wave. Specifically, we're going to focus on the wave height, the wave length. The wavelength is just the distance between one wave and the point, a corresponding point on an adjacent wave. A wave height is the difference between the top and the bottom of the wave. The top of the wave is called the crest. The bottom of the wave is called the trough. A wave period is the time it takes for one crest of a wave to pass between another crest, an adjacent crest. So the time between crests is known as the wave period. Here's a simple diagram. This is the crest. That is the trough, the low part of the wave. The wavelength would be the distance between one crest and an adjacent crest. Or actually, you can go between troughs as long as you take the corresponding point on an adjacent wave. That's a wavelength. The wave height, we take the crest and we take the height and we look at the distance between them. Simply the wave height. Okay, waves can be influenced by many things, including the wind's speed. As you might imagine, a wind with a higher velocity will produce a greater disturbance of a water surface. How long the wind blows. A sustained wind over several hours will produce more wave activity than short gusts that are separated by 30 minutes. And the fetch. The fetch is not what your dog does, but the fetch is the distance that the wind blows over continuous water. So the greater the fetch, the more energy that can be transmitted to the water surface. And that's why you'll get greater waves in a larger body of water compared to a small lake or a small pond. The fetch in the pond is not very long, whereas the fetch in the Gulf of Mexico is much, much greater. We have two different types of waves. We have a wave of oscillation where the energy will advance but not the water itself. Okay, and we have a wave of translation. We're going to look first at the wave of oscillation. Again, the energy is advancing but not the water itself. This is what occurs in the open sea. The individual water molecules are moving around in a circular pattern, a circular motion of the individual particles. There is more energy at the surface than there is at depth. Remember, if wind is primarily responsible for the production of waves, the interface is at the water-air surface. So therefore, you expect to have more energy at the surface, and the pass here, the little orbits, are much, much bigger, and they slowly decrease with depth. The wave base is usually located about 1/2 the wavelength. Remember, the wavelength is the distance between one point on a wave and the corresponding point on the adjacent wave. So if you take 1/2 of that wavelength and then move down from the surface of the water, that is generally the wave base. So at the wave base, this is about where all motion below that is essentially nil or zero. So you have this wave of oscillation, greater energy at the surface, it slowly decreases, and then below the wave base, about 1/2 the wavelength, we don't have much motion at all. It's essentially negligible. We call these waves in the open ocean swells. And I have a brief demonstration to show you a wave of oscillation. Okay, so here I have some dominoes on the table in front of me. They're plastic. I couldn't find the wooden ones. But note that I have all of these dominoes sort of lined up in a little sinuous path. And what's going to happen, I'm going to blow my wind I'm going to do the right side, because after taping a section on wind in deserts, we always had the wind coming from the left side. So I'm going to go from the right side. And what's going to happen is that the wind will impart energy to the first water molecule. So here we go. Now, what I want you to notice is that I have individual water molecules lined up on my desk, but you're not going to see my individual water molecules get up and walk, but you will see the energy move. Are you ready? Okay, here we go. Okay, so what happens is that the energy advanced across the desk, but each little individual water molecule was doing its own thing. It didn't move until I picked it up. So what's going to happen, these individual water molecules will make circular paths. As we move down from the surface, the circles, the orbits get smaller. And finally, at the wave base, it's nil. We're not going to have any motion below that. So what a wave of oscillation will do, it will transfer its energy in its circular motion from one water molecule to the other, and the wave will advance. However, the individual water molecules stay in the same spot. Let's get back to the PowerPoint. So if we look on this diagram again, note that these are going to be our waves of oscillation. These are the swells. They're gentle in open water. And also notice where the wave base is on this diagram compared to the actual movement of the particles. Note that the wave base is not intersecting any ground surface, any basin surface at this point. So we have the little individual water molecules making their little circular patterns, and the energy is transmitted that way. The molecules aren't moving. They're pretty much staying in their same spot except for this circular motion, but the energy is being transmitted. So here we have swells in deeper water. That's kind of to the upper right-hand part of that diagram. And they eventually encounter water that is more shallow than the wave base. So when that happens, that's going to disrupt their circular motion. And then we're going to see a wave of translation. In a wave of translation, the water itself is advancing up the shore. So the water's moving as well, not just the energy. What happens is that the speed and length of the wave, the energy of the wave, is then transformed to height because the little circular motion is disrupted. The energy has to go somewhere, and therefore it's transformed up to the height. At a critical point, however, we have too steep a wave and the wave will break. We call that breaking or surf. Surf is the turbulent water of breaking waves, an over steep wave. So the wavelength will decrease while the wave height increases because our circular motion of our water molecules is disturbed. The wave base is now lower than the surface of the basin that the water is encountering. So the wave height increases and it causes the waves to oversteepen and plunge forward as breakers. Now, to get an idea of the scale of this wave, check out some of those surfers for scale. Waves are refracted or bent as they approach the shore. They tend to become parallel to the shoreline, and in doing so, they're going to erode projections that are projecting out into the open water, and they'll eventually straighten the coastline. For example, here we have a headland that's sort of jutting out into a water body, and as the waves approach, they're going to impart a lot of energy to that headland. They're going to be refracted, erosion will occur, and over time we're going to see straightening of the coastline. Note in the bottom diagram we have now eroded quite a bit of that headland, that promontory, and there is deposition on either side of it in the form of sand in the bays. So the coastline is being straightened out by the waves. The water between the breaker zone and the beach will end up flowing parallel to the beach in the same direction as the approaching waves. So when this happens, we get longshore currents that are being generated that will flow parallel to the shoreline. So here's my incoming wave, and the longshore current is generated, which is going to flow parallel to the shoreline. And that brings us to our final shoreline process that we're going to investigate today, that of nearshore currents. We have a longshore current, as we noted, that is parallel to the shoreline. It can move sand. It's a great geologic agent. It moves sand in suspension and also gravel by rolling. This will be, of course, dependent upon the velocity and the energy of the longshore current, but in general, sand can be held in suspension and gravel is rolled along or slid along that beach. Rip currents or narrow currents which flow back out to sea. They're commonly developing where the wave heights are lower than they are in adjacent areas. Let's take a look at, this is the formation of a rip current. Note that it's a little narrow current that's flowing back to the sea, so we're getting the water back out from the beach. And sometimes you can pick out these rip currents because the sediment that's being transported back to the sea makes the water appear a little bit cloudy. Now, rip currents are also responsible for some of the signs you see along beaches. Danger, surf is unsafe, no lifeguard. Here we have a sign on a California coast that warns swimmers of dangerous rip currents, currents that are moving the water, transporting the water back out to sea. So when we look at these shoreline geologic agents, tides, waves, and nearshore currents are all geologic agents. They erode, they transport, and they deposit. Erosion processes will include corrosion, which is a chemical erosion of rocks, and hydrologic action. The force of the waves can erode quite effectively. Abrasion, any particles that are carried by the water in suspension or rolled along the surface can abrade quite effectively and erode. In Bodega Bay in California, hydrologic action and abrasion have undercut the sea cliffs with disastrous results for the human inhabitants. Some erosion features that are found along shorelines include wave-cut cliffs. The erosion by the surf at the base of coastal land will cause the cliff to retreat as it erodes. A wave-cut platform is that flat land that is left seaward of the wave-cut cliff. Let's take a look at that. So you can see the sea cliff that's residing on the right-hand side of that diagram, and what's happening is that the force of the water is building a wave-cut platform. Excuse me, building is a bad choice of words. It's eroding that wave-cut platform. As the sea cliff retreats, the wave-cut platform will grow. So the sea cliff is moving off in that direction, off to your right. Here's a marine terrace on the western coast of the United States. A terrace, a marine terrace, is exposed either by a relative rise of land or a drop in sea level. And basically the marine terrace is that wave-cut platform, that flat area that is eroded seaward of the sea cliff. And the sea cliff, of course, is retreating. If the sea level drops or the land rises, we see exposure of that wave-cut platform. That is a marine terrace. Other erosional features that can be seen on a shoreline include caves. The wave refraction around headlands will cause erosion on both sides of the headland, and a sea cave will form. If the erosion continues and the caves join on both sides of the headland, we get a sea arch. Continued erosion can result in the collapse of that sea arch, and then we have what's known as a sea stack. Okay, so we have a sea cave forming as we have erosion on both sides. We have a sea cave forming on both sides, and with continued erosion, if the caves join, we have an arch, a sea arch. And then out in open water, you see a sea stack. This probably was an arch that collapsed. Now this is kind of neat. This is a sea stack in Australia, and it has an arch that is eroded within the stack. Here we have some sea stacks. These are off of Shell Beach in California. Okay, so wave refraction and the longshore currents are primary geologic agents of transport and deposition. Let's look at the deposition features next. We've already looked at some of the erosion features. Now let's start with deposition. Beaches are simply a deposit of unconsolidated sediments. We can have discontinuous little beaches that form. These are known as pocket beaches. A continuous beach would be known as a strand, and this is where we have a longer section of deposition of sediments. Usually when we think of beaches, we think of quartz sands, but it can also be shell fragments, such as some beaches in Florida, or even basalt fragments, as in some Hawaiian beaches. Here we have a pocket beach. This is a discontinuous beach. Whereas a continuous beach is much, much larger. This is Myrtle Beach, South Carolina, and there is almost 100 kilometers of continuous beach. Now we think of beaches as those white quartzy sands, but this is a black basalt beach in Hawaii. If we look at a cross-section of a beach, we can come up with a common description or a beach profile. The foreshore of a beach is that part of the beach that is exposed to water. So this is any area that is wet during up until high tide. It can be dry for part of the day, but it is exposed to water during the day. The back shore of the beach is that area that only gets wet during storms or very, very high tides. Berms develop on the back shore, and these are platforms of wave deposited sediments. Let's take a look at that. So note that the foreshore is covered at high tide. So even though it's not necessarily wet all the time, it's exposed to water at some point of the day. The back shore, however, is dry. The berms are the sediments that are deposited on the back shore. And let me point out some berms for you. There we go. Beaches have seasonal changes. We can have a summer or fair weather profile, and a fair weather profile tends to have a very wide berm and a smooth offshore profile, while conversely a winter or stormy weather profile is little or no berm and has offshore sandbars. It's important to keep in mind that a beach can develop a winter profile at various times or seasons of the year. It's not necessarily confined to the winter. So look at the differences here in the berm. The summer profile is shown in blue. Notice how long that berm is, how developed it is, versus the red dotted line, which is the winter profile. But also notice what happens in the winter. The sand has to go somewhere, and look at the development of those offshore sandbars in a stormy weather or winter profile. In addition to beaches, we can see spits. These are depositional features. They are essentially the free arm of a beach or a sand that juts out into open water, and I'll show you a picture of that in just a minute. Baymouth bars develop when the spit actually closes off an inlet or a bay. So it's a sandbar that completely closes off a little water inlet. In this diagram, you can see the spit, which is forming to the on the left-hand side of the diagram. It is a jutting arm of sand into open water. Now, to the right side of the diagram, you see where a spit has moved continuously to close off an inlet, and at that point, it becomes known as a bay mouth bar. Look at the middle diagram, the recurved spit. This is a spit that has been modified by waves, so the free end is actually curved. Again, it's a recurved spit. It can be referred to as a hook. This spit is near Jenner, California. It's at the mouth of the Russian River. Here's a baymouth bar. It is completely closed off an inlet. Another depositional feature is a tombolo. This will connect a sea stack or an island to the mainland. So again, it's unconsolidated sediment deposition, and what happens here is that we have a little depositional sand body that connects either a little sea stack or a little island to the mainland. So the wave refraction around this island or sea stack is responsible for the formation of the tombolo. And here we'll see the the deposition between the island and the mainland. This is a tombolo. It formed along the Pacific coast of the United States. Barrier islands. Okay, so we have beaches, spits, baymouth bars, tombolos, and barrier islands. Barrier islands are narrow, low islands that are parallel to the shore. The formation of barrier islands is pretty heatedly debated. Some scientists think barrier islands formed as spits that became detached, or they might have formed as beach ridges on coasts that subsequently subsided or drowned. Some scientists propose they may have formed as remnants of old deltas as well. So here you see an overhead shot. Padre Island is a barrier island. Here's a close-up view of Padre Island, part of it. It's a popular beach destination in Texas. The Gulf of Mexico is the water body to the right-hand side of that photograph. Laguna Madre, the lagoon, is on the left-hand side of the photograph. It's on the left of the barrier island. The formation, again, is debated. Here we have a spit that may have become detached. That's one proposed mechanism. Another proposed mechanism is that we have a beach ridge, and then as the land was flooded, the ridge became a barrier island, and now we have a lagoon separating with a rising sea level, separating that former beach ridge, now a barrier island, from the mainland. We have different types of coastlines. We can have a depositional or an erosional coastline. This is categorized by sedimentation and erosion processes. For example, a depositional coastline would have wide sandy beaches and deltas and barrier islands, whereas an erosional coast would be categorized by steep and irregular landforms, sea cliffs, and wave-cut platforms. What we're going to investigate a little further is the submergent versus the emergent coast. And this is categorized based on a relative relationship with sea level. So it can be that a sea level is rising or falling, or that the land is rising or subsiding. So we're looking at a relative relationship with the sea level. In a submergent coastline, we're looking at a drowned coast. The sea level is rising with respect to the land, and one feature found in a submergent coast is an estuary or several estuaries. Estuaries are drowned river mouths. Chesapeake and Delaware Bays are both estuaries, and these developed when the east coast of the United States was flooded when the sea level rose at the end of the Pleistocene with melting ice, melting continental glaciers. Another submergent coast. This is a photograph of Louisiana's marshes. Estuaries are great fisheries, great fishery nurseries. An emergent coastline, conversely, occurs when the sea level is falling with respect to the land, and we see here features such as wave-cut cliffs and platforms, wave-cut platforms. So if you look at this photograph, this is the western United States coastline, and this is actually taken in California. How would you pick out that this coast is an emergent one? Well, there's a sea arch within a sea stack. There's a marine terrace in the background. So this is rocky terrain and jagged coastline. This is definitely an emergent coastline. Here's a great example of marine terraces. Remember the wave-cut platforms that are exposed as the sea level falls with respect to the land? These wave-cut platforms are exposed, and these are marine terraces. So this would be an emergent coast. Since so many people live along the coast, it's important that we manage coastal erosion. Unfortunately for Louisiana, it's the #1 state in coastal area loss each year. And coastal area loss can be attributed to many factors. For example, a rising sea level will affect the loss of coastal property. Subsidence occurs as sediments such as water or petroleum are pumped out, and the sediments that are left will compact and consolidate, and you'll get subsidence. Human activities, including the leveeing of the Mississippi River to keep the river in its channel, and the river control structures that prevent the delta from switching, now result in sediments that are being deposited beyond the coastal shelf in the Gulf of Mexico. So this prevents longshore currents from picking up those sediments and nourishing the coast and maintaining the coastline. Also, as oil exploration first began in the early 1900s, there were these different contraptions called marsh buggies, which were searching for salt domes that were in the subsurface. They weren't expressed topographically. So these marsh buggies went investigating to try to find salt domes that weren't very visible in the marsh, but could be detected. And as a result, these marsh buggies, their tracks are still part of the landscape in the coast. They decimated the marshes because they created channels for the Gulf of Mexico water to easily access the marsh, and then the erosion continues along the channels as more and more sediments are being swept away and the channels are enlarging. And hurricanes, of course, have also decimated the marshes as well. Hurricane Katrina 2005 was responsible for a lot of damage in Mississippi and Louisiana. This scene is from Biloxi. Most of us probably watched with horror the terrible chain of events that unfolded in New Orleans as well after Hurricane Katrina. The cheniers at the mouth of the Mississippi River were destroyed by the storm surge of Katrina. This is the Chandelier Islands in 2001. Note the arrow for reference. And this is August 31st, 2005. Same Chandelier Islands. Note how much is gone. Let's do that again. Before Katrina, after Katrina. Huge, huge problem. So how can we manage coastal erosion and possibly prevent coastal erosion? There are some prevention measures that are employed. Some of them are more effective than others. Some of them are a lot more expensive than others. One is beach nourishment. This involves simply pumping in sand to replace the sand that was lost to erosion. Groins are barriers that are perpendicular to a beach line, and they are put in to trap sediments. Let's take a look at those first. These long jetties, if you will, that are jutting out from the beach, these are groins, and they trap the sediment that's being transported by the longshore currents. Now, of course, the bad thing is if you have property along the coast and your neighbor puts up a groin to trap sediments, you don't get any on the other side of the the longshore current. So that can create some problems among property owners when some property owners feel that their sediments are being trapped and not going to their property, but instead being hogged by their neighbor. In which direction do you think the longshore current is flowing in that photograph? Okay, there you go, because you see the deposition up against the groin. So you know that the longshore current is flowing from the bottom, kind of the bottom right of this photograph. Sediments are being trapped against the groins, and look what happens on the down current direction of that groin. There's very little sand that is on that beach. Instead, it's accumulating against the groins. So you can imagine if your neighbor puts up a groin at the edge of his property and traps all the sediment, you might be a little upset with that. Beach Nourishment Program was established at Miami Beach. Here is the beach before the sand was pumped in. And there's the beach after the sand was pumped in. So you can just about imagine the volume of sand that was involved here. Of course, this is not an easy process necessarily, and it's not a cheap process, and it's not a permanent solution, because what's going to happen to that sand? It's again, we're still going to see erosion and transportation and deposition elsewhere, so it's not a permanent solution. Beaches are features that are continuously modified on the earth and have changed drastically over time in Earth's history. Another potential for coastal erosion, and also as hurricane protective measures, involves seawalls. These are more massively constructed items than groins, for example. One of the most famous seawalls is in Galveston, Texas, and it was constructed after the leveling of Galveston by the hurricane that ran ashore in 1900. So the seawall construction began in 1902. Now, the wall is designed to deflect waves, sea waves, upward. Note the curve of that wall. That's kind of neat. And it's still being maintained. Here's a more modern view of that seawall. Other prevention measures include adding riprap, concrete or rocks, and building artificial berms. These are cheaper solutions, but they're not necessarily permanent solutions. This is riprap that's piled up to protect a hotel. The hotel's actually to the left of that photograph. You can't see it in the image. And here is an artificial berm that's being constructed. Note the earth-moving material, the earth mover moving the sand, and he's to the right of your photograph. But this berm on the Isle of Palms in South Carolina is being built, but it needs to be rebuilt every 2 weeks after each spring tide. So it's not permanent, and it does involve constant maintenance. Unfortunately, barrier islands are not permanent features, and they will move. They will migrate as sea level changes. So when the sea level rises, the barrier island will actually migrate landward. This is a natural process, and the islands will shift. Of course, for the people who are inhabiting those islands, it can be a problem. Here we see a barrier island, the lagoon separating the island from the coastline. And what happens with sea level rise? Well, guess what? The barrier island will migrate and move toward the land with rising sea level. And again, this is a natural process, but when you have huge multi-million-dollar hotels and resorts built on the barrier island, it's an expensive natural process. True life example, jetties that were constructed in the 1930s to protect Ocean City, Maryland's inlet access disrupted the longshore currents. So the island was essentially starved of sediments, and it began to migrate landward. It migrated 500 meters toward the coast. In 2002, beach sand was brought in an effort to replenish the sand, and the jury's still out on how effective that is. Well, that will conclude today's lecture on seashore processes. We've looked today at shorelines, we've looked at tides and waves and nearshore currents. All of these are geologic agents which have greatly modified the coastlines throughout Earth's history. This is only an overview, so if you have any questions, please feel free to post them on your discussion board or email your instructor. Thank you so much for joining me, and have a great day.